So, let us start that part 2 of design of columns. In the last class we have stopped, we are discussing that second assumption specifically for compression members. It says the maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, and when there is no tension on the section shall be 0.0035 minus 0.75 times the strain at the least compressed fiber. So, let us draw the cross section. Okay, I think let us make it. So, we can have this is the cross section of a column, and it says that if, let us say, assume this is your maximum compressed side. Let us assume this is your maximum compressed side. When it is possible when there is that bending is acting on the column. In addition to the axial load, that bending also there. So, what we can do? What is the case then? The case here we can say there is no tension. There is no tension here. If there is no tension, how far shall we go? Let us assume this is the strain diagram, this is strain diagram, this is the cross section B and D. I am telling that maximum allowed say 0.0035, this is the one maximum strain. In any case we cannot go, because concrete cannot take more than 0.0035. So, we can go up to 0.0035, and also I am telling that this side there is no tension. That means, this is the one we can have, because if we have somewhere we can have, so that means the tension may occur. So, I can have this limiting value. So, from this end to this end I can have. Where will be then your 0.002? 0.002 it will be somewhere, say here. So, 0.002 from there we are getting that, and 0.0035. What we can do it here? We can get somewhere here 0.002 the strain. So, how much is this portion? We have two parts. One part is 0.002 means it will be 4/7, and this portion 3/7, 4/7 and 3/7, because 0.002 and 0.0035. So, this portion is nothing but out of 4/7, this one and this one 3/7. In other way I can say this is 4/7D and this is 3/7D. The 3/7 of D and this is 4/7 of D. So, we can have this one. Now, what we say that as if this line will move, rotate with respect to this point, because if we rotate about this, or we can rotate about this, if we rotate about this, then what will happen? Then our strain may be increased, it will go beyond 0.0035. So, this is our pivot point. If we take this is our pivot point, it means, because I am not telling that we are deducting that one from this assumption. So, assumption it says that if we can rotate about this point like this, then we shall get one strain here which will be less than 0.0035, and the other strain is developed. This is the least side, that compressive side, and this is the maximum stress of compression side. So, we can find out, and that one will be equal to, that means, if I know this one, if I know this value, then I can find out this one, which is nothing but, let us say, epsilon least compression, and this one is will be equal to 3/4 of epsilon LC. So, 0.0035 minus this one will give me the strain here. This is the strain which I am interested to find out. So, I can get 0.0035 minus this one. So, that means it is pivoted about this point. What is the pivot point? Pivot point is from the maximum compression side at a distance of 3/7 of d. At a distance of 3/7 of d, there we are getting 0.002. With respect to that, our stress strain diagram, that one rotates. So, I shall get a certain compression strain here. So, corresponding one I shall get it 3/4, which is nothing but 0.75. That is why our code says the assumption the maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, that means axially loaded as well as bending also there, and when there is no tension on the section shall be 0.0035 minus 0.75 times the strain at the least compressed fiber. So, this is your least compressed fiber and this is the maximum stressed. So, that one we shall get it considering 0.0035 minus 3/4 of this one, that way you can find out. Now, how shall we get this value? How shall we get this value? This value we can obviously this value we shall find out depending on the situation where is the neutral axis, because I know this point, so we can find out that where is the neutral axis, that we can find out, and accordingly we can find out this strain. Why it is so important? It is important because what we do it for uniaxial bending. If uniaxial bending, that means the only moment is acting about this axis, say, that is called uniaxial bending, and also axially loaded. What we can do? We can find out from this strain diagram as well as from the stress, we can find out what is the capacity of that particular, say, your column. That we can find out capacity of that column. So, that is called actually your interaction diagram. So, we can find out that interaction diagram on the basis of this, say, your strain diagram, we can find out an interaction diagram we can find out, and which will be useful for design of columns for uniaxial bending cases. Similarly, we can go for, say, biaxial cases also. Now, let us come that what is the permissible stresses. Let us come that what is the permissible stress, and accordingly let us find out how much load it can take. That means, the section you are providing, so how much your that maximum load, that is a PU it can take. So, axially loaded column, so if we take, say, your 0.002, so we are getting that one, which is nothing but we can take 0.45 FCK. We can take it as 0.45 FCK. So, what is the value of P then? P will be equal to area of concrete, AC, area of concrete times 0.45 FCK. If we take a section, here, let us say we are having this steel. So, we are having, say, B and D. AC, area of concrete, let us say B times D. Area of steel will be equal to, that if you have 4 numbers or 6 numbers, whatever numbers of that, from there you can find up area of steel, that you can find out. So, P will be equal to AC times 0.45 FCK, because we are talking strain 0.002. This is the one our code says for axially loaded column that your direct compression it is 0.002. What we have to find out then? That means at 0.002 strain, what is the corresponding stress in concrete as well as in steel? So, in our case it says we already have achieved that maximum allowable and that is 0.45 FCK. So, 0.45 FCK. So, area of steel, so area of concrete times 0.45 FCK, that is the one that load it can carry, that concrete can carry, plus what about your that area of steel times at 0.002 for Fe 415. Here it may be different for steel grade, for different steel you will get different type of different your stress at 0.002 the stress will be different. If it is say your Fe 415 for 0.002 corresponding stress 0.75 FOI, for Fe 250 0.002 that already we have achieved, that is 0.87 FOI. So, we shall get that two different formula for 415 we shall get one, for 250 we shall get another one. So, if we take now for Fe 415, so let us write down here for Fe 415 we are talking this one, then area of steel will be equal to maximum load it can carry this one for concrete plus AS times 0.75 FOI, but already we have taken that concrete portion. So, let us remove that concrete that area, which is nothing but instead of that we can make it say 0.45 FCK. Area of steel 0.75 FOI minus 0.45 FCK, because we have already taken that one for concrete certain one. So, that is why either you can do it like this, A dash C I can say A dash C equal to AC minus AS, that way also we can do it. In that case I need not what is called that one subtract it here, but in other way we can do it here, that AC times 0.45 FCK plus AS times 0.75 FOI minus 0.45 FCK for Fe 415. Okay. Now, what about your Fe 250? For Fe 250 that same P will be equal to AC 0.45 FCK plus AS times already I have told 0.87 FOI minus 0.45 FCK. So, P equal to AC times 0.45 FCK plus AS times 0.87 FOI minus 0.45 FCK. Here that is the difference, we will get it here. Okay. Now, what we do? We assume that it is within the axial loaded will be within 5% of lateral dimension. That means, this P is being acted here within 5% of lateral dimension. That means, let us say 0.05 D. I can say that means it will act, then we shall consider this one as a axial loaded column. That means, we shall not take that eccentricity. If it goes beyond that, in that case you have to the load applied P multiplied by that eccentricity will give me the corresponding moment. But here what we are doing, since we are talking say axially loaded column, so we can go up to 0.0, that means we are not necessarily at this midpoint, it can go, how far we can go, that 5% of the lateral dimension. So, 0.05 D. If due to construction error or whatever it is, it will happen, and then we can go up to 0.05 D. That is why what we do, we consider that P equal to, I can now come back to your say your clause 39.3. So,
for the transverse side, it's same limit of 5% of DO.
yes, we can go say maximum say 5% that our code says. So, 5% we can go.
That is on this way.
Yes,
What
both
about
sides.
this way?
The other side also we can take say 5% that way, yes. So, P equal to here we can take that value as 0.9 times point, we are taking 90%. Because of this we are taking 90% of the value. So, 0.45 FCK times AC plus, if we ignore the other value 0.75 FYS, I mean to say if we ignore this portion, then I can get 90% of the this value, we shall take it as the allowable one. Because since we know that we shall not be able to construct it, within that you say without any eccentricity. Even if we know that it goes say maximum 5%, in that case we are reducing this value. That means, if we provide a section with some reinforcement on the basis of what is the maximum allowable load, that we can compute. That means, whatever value you have computed, you take 90% of that. If we take that 90% of that, then what we will get it here? P will be equal to, so 0.9 into 0.45, 0.4050 FCK times AC plus 0.9 times 0.75, 0.6750 AS. So, whatever we have done it here for say this value axial loaded column for Fe415, we can get this one. If we ignore this portion, then we can get say 0.45 FCK AC plus 0.75 FYAS. Now, since we shall not be able to construct it without any eccentricity, will come on the even for due to construction also. So, that is why you are taking that maximum allowable load, let us say we shall take 90% of that. So, whatever we have calculated, you take 90% 0.9. So, we are getting 0.4050 FCK AC plus 0.6750 AS. Now, our code says that is in clause 39.3 page 71 IS 456 2000. Our code says it is PU equal to 0.4 FCK AC plus 0.67, sorry, here Fy is missing, FYAS. So, our code says that 0.4 FCK AC plus we have reduced this one, say another 5 that one. So, we can come to that 0.4 FCK AC plus 0.67 FYAS. So, this is the maximum allowable. That means, if you know a section certain dimension B and D, and you know that you have provided steel. So, we can find out that what is the corresponding maximum allowable load it can take, that is Pu, using this formula for axial loaded column. Similarly, we can find out for say your uniaxial other cases that we can do it, but anyway. So, this is the case for axial loaded column that we have to do it. Okay. So, the design of column is very simple in that case. So, what we have to do? Let us take one section, say 250 by 300. Let us take a section 250 by 300, and let us take I am giving here say 412 torr. okay. B equal to 250 millimeter, D equal to 300 millimeter, AC equal to 250 times 300, AS equal to 4 times let us say, let us find out the percentage of steel before going to the calculation. Percent of steel equal to which comes as 0.603 percentage. So, even if even say this section can take the load whatever you are applied, even then we cannot provide this section with this reinforcement because it is less than 0.8%. First one, that whenever even say we can calculate this one according to this formula, that Pu, let us find out first. Pu equal to 0.4 FCK AC plus 0.67 FYAS. Let us take FCK equal to 20, M20, Fy 415 Newton per square meter for Fe 415. So, Pu equal to 0.4 times 20 times 75,000, that is the one we have got it, plus 0.67 times 415 times 452. Okay, I think it should be stopped there at 452 only. Anyway, so we are getting here 0.4 times 20 times 75000 plus 0.67 times 415 times 452.38. We are getting here 125784, say. Let us make it like this, Newton. So, we can find out here let us say 725 kilonewton. That means, the Pu is maximum allowable 725 kilonewton. This particular one we can get it say 725 kilonewton. What we shall do here, maybe in the case here that your section, it can take that load actually applied less than 725. What we can do, we can reduce this one say 250 by 250 also, that also we can do. We can reduce it that 250 by 250 also, that we can do also, and we can find out whether we are getting that what is the value of Pu. Let us try that one at least. So, if we take a square section 250 by 250 the same way. So, AC equal to 250 into 250 equals 62500 millimeter square, and AS for 412 torr we are using the same one, which is coming as say 452 square millimeter. We can go 452.38 all those things, but anyway. So, 452 we can take it. So, Pu equal to 0.4 times 20 for M20 grade of concrete times 62500 plus 0.67 times 415 times 452, which comes as 0.420 into 625. So, and the other one 0.67 times 415 times 452, which comes as 125,678 say Newton, equals 625.678 kilonewton. So, we can get Pu this one, but what about the percentage of steel? Equal to 452 divided by 62500 times 100. So, 452 into 100 by 62500, 0.7232. So, this is the percentage of steel, that is even if 250 by 250. Generally, what I mean to say here, most of the cases you will find out this is a very standard practice that they that mason all those things in general building, what they do that 250 by 250 and use 412 number of bars. But according to IS code, even in that case it is very less, the value that is less than 0.8. So, we have to follow those that codes, that what exactly you will get it here, that you will get it in, because it is very important. And here generally we check those things. The calculation, it means that in design of the concrete, I repeat, reinforced concrete, the bending moment, shear force or axially loaded column, axial forces, all those things you will find out it is very less. But even then you have to provide certain minimum one from the say your crack, shrinkage, creep, and lot of other things also involved, stability. So, from their point of view you have to provide that minimum reinforcement. If you have to provide the minimum reinforcement or minimum dimension that you have to provide, and for that you have to follow IS 456. If there is any dispute, then obviously if you follow according to this code, then nobody can say that why you have used that much. So, this is the very important. It is not necessarily that it is just simple mathematics that you are using formula, getting thing and you are providing it. It is not that one. It is much more than that, where you have to provide that one that restricted by say minimum reinforcement, that you have to follow. So, here excuse me.
What was our motive actually for checking for two sections?
What I am trying to say, I have initially I have taken say 250 by 300 and I have used 412 number of bars, just arbitrarily I have taken. Then even then I am coming to say 250 by 250. What I mean to say here in this case, in most of the cases you will find out that people are using 250 by 250 section and 4 number 12 bar, that is very standard practice you will find out. So, in that case what I have found that it is not as per IS code.
So, the minimum percentage should be
0.8. So, let us come now to the your code, and that you will find out in clause 26.5.3, that columns, page 48 IS. I am always referring this one so that you will be familiar with these clauses. So, what it says, the first clause that A, the cross-sectional area of longitudinal reinforcement shall be not less than 0.8%, minimum reinforcement not less than 0.8% and not more than 6% of what? Of the gross cross sectional area. Okay. So, this is your basic thing that 0.8% should not be less than, that means in our case 255, that one is that very less. Let us say 6 times 113, that means 6 number of bars, let us consider, divided by 62500. So, it comes say 1%. If we use say 6 number of bars in 250 by 250 section, so it comes 1.08% that it comes. So, at least we should provide say 6 number of say 12 bars that we can provide here, because other next higher we are having because next higher is your say 16 dia bar, but if you use say 4 16 number 16 dia bar if you provide, which is coming as 1.28%. So, in the practical cases say 250 by 250 section, we can provide the minimum reinforcement that we can provide say 6 number of 12 bar if we provide, then in that case it is coming 1.02%, but even then we can provide, though it is going little more than 0.8%, but that is the one we can provide. So, this is the one that we should always follow. The minimum number of bars, minimum number of longitudinal bars provided in columns shall be 4 in rectangular columns and 6 in circular columns. So, 4 numbers, minimum 4 numbers in rectangular column and 6 numbers in circular column. The bars shall not be less than 12 millimeter in diameter. Less than 12 millimeter in diameter. Okay. Then we can have spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 millimeter. That means, we can have 300 millimeter, that is the one that gap between maximum gap between the longitudinal bars. Okay, that if it is more, then we have to provide that 2 number. Even if you say reinforcement or say it is not, that means what I mean to say, it is not dependent on only the strength point of view, the load applied. It is dependent on so many other guidelines also, that minimum number of bars, then your say bar diameter, then your this restriction say 300 millimeter, all those things. Say sometimes it may happen that whatever the reason, the column dimension from practical point of view or whatever the case, the dimension is more say maybe say 500 500, that you have to provide. Okay. So, if you have to provide that dimension, then you have to provide the reinforcement. In that case, what we do, we know the load is not coming more, the load is very very less, which can be accommodated in 250 by 250 section, but since it is 500 500, so you have to provide the reinforcement that 0.8% of that 500 cross section. So, in that case, you know that it will, the strength is more coming more, but even then we can't help it, that we have to use it, and that we have to do it according to this IS code. Okay. Similarly, that not only that, you have that bar diameter also you cannot provide say 8 millimeter, we have to provide not 10 millimeter, we have to provide say 12 millimeter. So, this is your case. Now, I shall tell you regarding say lateral ties. That means, the way we consider in beam that is stirrup, here we call it say tie. So, the least lateral dimension pitch of or spacing of lateral ties, number 1, least lateral dimension of the compression member, number 2, 16 times the smallest diameter, 16 times the smallest diameter of the longitudinal reinforcement. If you have say 12 and 16 all those things, so it will be dependent on the minimum least of that, or number 3, 300 millimeter. So, we have least lateral dimension, that is one case. Then another one we shall find out whatever the longitudinal diameter you have provided, multiplied with the 16 one. If you have say 12 millimeter, 16 millimeter like that, out of that you take the smallest diameter and then you find out the 16 times of that, or 300 millimeter. Out of this, which one is the minimum that you have to provide. So, this is your lateral ties that you would say pitch or spacing, that means what will be the spacing that you have to provide like that. But what about the diameter? The diameter 1/4 not less than 1/4 of the dia of the largest longitudinal bar. Please note here, for spacing we have taken the least and for diameter we are taking the largest. If you have 12 millimeter, 60 millimeter, all those things, so you have to take the largest one. Okay. So, this is the case we have to consider here, 1/4 of the diameter of the largest longitudinal bar. So, with this what we have to do, with this we have to design our. So, that means we know now we know the restriction, and with this we have to design your say that your what is called that compression member. There is another one we can have, that is called your say, because you can find out, it is very simple, that you can find out, you provide that one. First what you have to do, number 1, you find out the effective length of the column, then on the basis of that you find out what is the dimension of the column. If you would like to design it as a say short column, then it will be restricted by say LEX by L by D, that is should be less than 12. So, you can give that your say dimension of the column also, and what we can do, if you assume that it is a 1% steel, let us assume the other way also we can do it, we can find out that 1% steel. Our design calculation is very simple, that Pu, let us say one way, let us say Pu equal to 1200 kilonewton say, that is we have computed from any, that is from analysis 1200 kilonewton, M20 grade of concrete, Fe415, that we have done it. So, this is your case. What we can do, we shall find out, we know Pu equal to 0.4 FCK times AC plus 0.67 FYAS. What we shall do it here, we can assume that we shall use 1% steel. So, we can say AS equal to 0.01 AC. Okay. So, we can write down here 0.4 FCK AC plus 0.67 FY times 0.01 AC equal to Pu, because I can now calculate AC also, or 0.4 times 20 times AC plus 0.67 times 415 times 0.01 AC equal to 1200 into 10 to the power 3. I am making it in all in Newton, or let us find out 0.4 into 208 AC plus 0.67 times 415 times 0.01, 2.7805 AC equal to 1200 into 10 to the power 3, or 10.7805 AC equal to 1200 into 10 to the power 3. Okay. So, AC we can find out. Therefore, 10.7805 AC equal to 1200 into 10 to the power 3, AC equal to 1200 into 10 to the power 3 by 10.7805 10.7805 equals 111,312.09 square millimeter. If you use say square column, D comes as 333. So, we cannot provide this one. What we can do it here, let us assume that we are provide 350 by 350, provide 350 by 350 dimension column. So, AC equal to, we are getting here 350 into 350 comes as, so 122,500 square millimeter. AS equal to 0.01 times AC, because we are providing this one. So, 0.01 times AC, (1225) square millimeter. So, AS equal to 1225 square millimeter. If we take, which is coming as, if we use say 12 torr, numbers 10.84. If you use 16 torr, number 6.09, 12 torr 10.84, 16 torr 6.09. What you have to do it here, if we go for say your 12 torr, then we have to go at least 12 numbers, because 11 numbers we cannot provide. So, we have to provide say 12 numbers. If we go for say 16 torr, then we shall go say not say 6 numbers is not possible. So, at least we have to provide say 8. So, in that case you can find out even then also how far we are, just 1200 kilonewton to accommodate that, how far we are deviating. So, in that case, so it is not the one that there is any tolerance. So, you have to go restricted with that one also, the number of bars. So, we can provide say 16 torque say. Let us provide. So, let us provide 8 16 torque, dimension 350 by 350, okay. Then S equal to 8 so percentage of steel. So, percentage of steel we are getting here. So, 1608 by 350 by 350. So, that means we are going to 1.31 percentage. So, in that case we are going up to 1.31 percentage. What about then lateral ties? Lateral ties, we can say 1/4 of 16, but there is no such 1/4 times 16 is 4 millimeter. There is no such bar. There is no such bar of say 4 millimeter. So, use 6 millimeter, and that one will be here phi, that mild steel, because 6 millimeter torch steel is not available. Torch steel is available only from 8 millimeter. So, we can provide 6 millimeter, even then we can provide. What about the reinforcement? Sorry, that spacing. The spacing, we have 3 different cases. We have 3 different cases. We have number 1, that your least lateral dimension, which is here spacing. So, least lateral dimension, which is here 350 millimeter. Number 2, 16 times the diameter, which is coming as 256, and number 3, that 300 millimeter. So, out of that we are having 256 is the minimum. So, let us provide 6 phi at the rate of 250 center to center.
So, we cannot go below 256, sir.
We cannot go?
No, we can go.
We are giving 250. So, it should not be more than 256. So, here it is coming say your 250. So, this is the one we can do. So, we can provide, finally we can do it. We have to provide one say cross section like this, and we have provided 8 bars in 8 corners. First we have to provide, and since it is axially loaded, so we can provide in all 4 sides, and we can provide here the tie. We can provide here tie, and also we shall provide here tie here also, for this one also, not only for the outer one, for inner one also you have to provide. So, this dimension 350, 350, and let us provide here this bar. So, we can have one bar outer side, another bar here, other bar here. Then we can find out that like this, and let us provide here one. I mean to say this gap is 250. That means, I am not providing the one I showed it in one, that I do not want to provide at the same level. I would like to provide this one say at this level outer one, and this one I would like to provide say at 125. So, this gap will be 125, but it will go again at 250 interval. So, that way it is easier to bind it. So, that way I prefer that one, but but the other one also correct. It does not mean that that is wrong, that is also equally correct. So, we are getting M20 Fe 415, should write down clearly, steel, and main reinforcement eight 16 torr tie 6 at the rate of 250 center to center. So, this is your that design that you have to provide, so that your draftsman can make the drawing from here. Okay. So, this is all that retaining say axial loaded column. So, we shall go in the next class, we shall continue with the uniaxial bending. Okay. Thank you.